The biggest piece of advice I can give you in lab is when you are connecting your op-amp circuit, connect plus and minus 15 to pins 7 and 4 and leave them and don't touch them again for the rest of the day. Your op-amp, that's part of your op-amp that doesn't move, doesn't change, and doesn't figure into any equations whatsoever. So you never use plus or minus 15 as an input or an output or a consideration. It just is what runs the device. So do that first and then don't change it. So when you change your circuit, don't move that, leave it. Also, use as few wires as possible. Most of these circuits are possible to make with just resistors connecting to places without connecting a bunch of wires. That's probably my biggest piece of advice. Then you can, and also if you can build the first circuit before you get there, that also helps quite a bit. The good thing is, we're going to talk about several different circuits this week. They are all pretty much based on the same actual circuit. So most of them, pretty much all of them, are types of inverting op-amp circuits. The inverting op-amp circuit that we've done already is actually the basis for a whole bunch of different applications. Also, the circuits that I'm going to cover in the first lecture here are identical to the ones in the second and third, but have completely different applications. So as far as what you're looking at, they'll all kind of look the same for the most part, but how we use them is going to be different. Hopefully, if you never studied filters before, you watched the video from last week that just goes over how filters are plotted and such and so forth. You usually get that in circuits too. And passive filters, I think, are studied there, where you just have, say, a resistor and a capacitor, or an inductor and a resistor, or whatever. And all filters do is they allow some frequencies to pass and they block other frequencies. They generally come in low or high pass types, or band pass and band stop, but we don't cover those in here. We just do basically low and high pass kinds. So passive filters are constructed just with passive elements. They use just elements that you would encounter in circuits too. Active filters add an op-amp, and by adding an op-amp, they increase stability, which is nice, and they have a lot of other types of advantages. We use resistors, capacitors, and op-amps. You can use inductors, but inductors are huge and lossy, and so we generally don't use inductors in these circuits. So basically, all the circuits this week are going to have the addition of a capacitor in the circuit somewhere, which of course changes everything, because then you have to worry about complex numbers and you have to worry about imaginary stuff, but it's not terrible. So the nice thing about active filters, first of all, in a normal passive filter, you basically are creating a complex voltage divider, is what you're doing. You're creating a voltage divider that changes with frequency because the impedance of the capacitor changes. So you always lose signal. The nice thing about an active filter is it actually can increase the signal as well as filtering. So it doesn't attenuate the signal automatically, which is good. When you add a load to it, it doesn't change the output. We've already seen that with inverting amps, non-inverting amps. So you can add something to the output and it doesn't change what it is. They're small, they're inexpensive, and there's lots of ways to design them, way more than I'm going to cover. I'm only covering two. When I was a student, I took a whole entire course in active filters, and the book was this thick, and it had all kinds of active filters that you can make out of op-amps. So we cover the most basic of basics. So they do have disadvantages as well. You have to have a DC power supply, obviously, because it's an op-amp. So it makes it a little more complicated as far as running them, because you do have to have a DC power supply. Also, they're not good for large signals because they can't process anything bigger than the DC power supply connected. So they're not good if you have outputs of 50 volts or 100 volts. You can't use an active filter for that. It's got to be relatively small signals. And at high frequencies, you do have issues with attenuation due to the op amp. The op amp itself often has a high frequency limitation, and when you get to a certain frequency, you can't quite process the signal. So we're going to look at two types, what's known as first order low pass and first order high pass. There are higher ordered filters, like I said, there's whole books, but first order just means we have one op amp, and the way it basically is based on how the transfer function ends up coming out with no squares or cubes or anything weird like that. So that's basically why they're called first order. So we start with the inverting op amp circuit. Hopefully you recognize this by now automatically. The only difference here is that instead of resistors, we now have complex impedances. The way we calculate the gain is the same way, it's just more general. It's just minus Z2 over Z1. And that can make it kind of weird when we start to actually create filters. So for a practical low-pass filter, one that will work and work well, what we do is Z1 is just equal to R1. That will just still be resistive. But Z2 is actually going to be a parallel combination of a capacitor and a resistor. So it's going to look like that. In order to figure out what the value of the transfer function is, and this is going to be a frequency-dependent transfer function. So instead of just giving us an output that's based on the ratio of resistors, it's going to give us an output based on the components, but also based on whatever frequency that we're using in the circuit. So Z1 is R1. That's relatively simple. And Z2 is just R2 in parallel with 1 over j omega c. So we basically just put R2 times 1 over j omega c over R2 plus 1 over j omega c. And then the standard procedure is to simplify it by multiplying everything by j omega c. And that is what we get. We get R2 over j omega R2c plus 1. Now, that is only Z2. Now we have to actually figure out what the overall gain is. So we have to take Z2 over Z1 and make it minus. So we do that, and we put it in, and we do a little bit of simplification. And as you can see, we just put 1 over R1 and multiply it by whatever Z2 is. And then what we do is we actually take R2 off the top and we put it out in front, which is actually kind of cool because that is the gain when you're at very, very low frequencies. When you're at really low frequencies, the capacitor just looks like an open circuit. And because it looks like an open circuit, you end up with your original inverting op amp circuit again. So at low frequencies, it all reduces down to minus R2 over R1. And then as the frequency increases, the impedance of the capacitor has more and more of an effect on the circuit. So what do we do with this? Well, there's one thing that if you studied filters before, you need to know, and that's when does the filter actually start filtering out values? So when do we get to the point, or what is the frequency at which we start to actually have attenuation of the signal? So we have to, for that, find the break frequency, or what we call the half power frequency. We call it the half power frequency because half the maximum power is being delivered to the load. This has all kinds of different names. It can be called break frequency, half power frequency, corner frequency, what other ones can it be called? It can be called minus 3 dB frequency. When you did the LT Spice Lab and you were finding that 3 dB less than the maximum, that was what was the break frequency. That's what you were finding when you did that. So what we do is we take the magnitude of the gain and we set it equal to 1 over square root of 2 times the low frequency gain, which is just 0.707, which turns out to be, if you calculate the dB value, that ends up being 3 dB or minus 3 dB. So we find the magnitude, and then we go ahead and set it equal to 1 over square root of 2 times the low frequency gain. So when we do that, we don't worry about, we're now sort of taking the imaginary part out of it, which is good. We don't have to work about imaginary numbers in here. So the magnitude is R2 over R1 times 1 over the square root of omega R2C squared plus 1 squared. We set that equal to R2 over R1 times 1 over square root of 2. You notice we've taken the negative sign away, and we generally do that with most of these signals because now it's complex. The negative sign means a phase inversion, not a negative number, so it kind of doesn't matter. We just use the magnitude of the gain pretty much when we're talking about filters and other things. So when we do that, we've got R2 over R1 on both sides, so we can get rid of those. And you will see a reference to passive filters because this actually does come out to be really similar to that. We basically end up with the omega R2C equals 1 in order to make this equation come out, since we have 1 over something plus 1 equals 1 over square root of 2. So that means that the break frequency is 1 over 2 pi R2C. And you've seen 1 over 2 pi RC before. When you do passive filters, that's how you find the break frequencies. You just do 1 over 2 pi RC. The thing that gets confusing when we're dealing with active filters is which R do you use to find the break frequency? The R that you use is the one that is actually physically connected to the capacitor. So you don't use R1. Actually, R1 has no effect at all on the break frequency. So you always use the resistor that is in the closest proximity to the capacitor. You can actually make a kind of a low-pass filter without R2 in there at all, with just the capacitor and the R1, but that's unstable and doesn't work very well. So the resistor R2 is added in order to make sure that the gain at low frequencies doesn't go up towards infinity, because it becomes more and more and more of an open circuit. So now that we know that, we're going to go through just a small example of designing an active low-pass filter. And we're usually, when we deal with filters, given some types of qualifiers or standards we need to address. We want a low frequency gain of 20 dB, which means that R2 over R1 is going to have to equal 20 dB, and a break frequency of 10 kilohertz, and we are given the value of the capacitor. Almost always when designing active filters, you pick a capacitor and start with that, because capacitors don't come in as many values. They have a wider range as far as their tolerance value, so usually we start with that, then figure out the resistors and get as close as we can. So R2 is easy to find. We know what the break frequency is, we know what C is, so we just go through and calculate that. We get 33.863 kiloohms, and we'll continue to use that number for a minute, even though there is no resistor of that value. And then we have to find R1. To find R1, we have to convert the gain back to a real number. And remember, to convert dB to regular number, we just take 10 and raise it to the dB power divided by 20. So we're going to end up with 10 to the 20 dB over 20, and we get 10. And then we just solve for R1 because we know the low frequency gain is supposed to be 10. So R1 is R2 over 10. We get 3.386 kiloohms. And then we just convert those to standard values of 3.3K and 33K. But after you're done, you basically test the circuit. And this one was run through LT Spice. And when you do that and you get an output, you can actually look and see the low frequency gain is 20 dB, which is what it's supposed to be. And then somewhere over here, we have minus 3 dB, and we go down and figure out what that value is, and it is actually 10 kilohertz, which is good. If it wasn't, I would feel bad. So that is the low pass filter. Cool thing is the high pass filter is almost exactly the same. In fact, everything else we do today is almost exactly the same. That's probably the hardest one. And we'll talk later about what can happen in the part where the slope is. Right now, if we were going to run a low-pass filter, we would have to have frequencies under 10 kilohertz, and then it would just pass through unimpeded, and anything higher than that would just go away. Yes?
How do you make that slope steeper?
You can't. Well, okay. With a filter like this, the rate at which the roll-off occurs is minus 20 dB per decade or minus 6 dB per octave. And you can't change it with this circuit. However, with other active filters, you can change it. There are ways of making higher order filters where you can make a really, really steep roll-off. And the weird thing is they move along and they roll off, and then a lot of times they bump up and have little rings down at, very, very low values. But they don't just drop, but they do at some point are able to do that, but not with this particular circuit. That's all you get. High pass filters are almost the same. The only difference is we moved the capacitor, which means at some frequency we're going to end up with R2 over R1 again, but it's not going to be at low frequencies. So this time Z1 is R1 plus 1 over J omega C, and then we can actually move things around a little bit, and we get J omega R1C plus 1 over J omega C. So it looks sort of similar to what we had before, a little bit different. And then Z2 is R2. And we again can take V out over V in. We do the same thing. And this time, when we put them together, it comes out a little bit differently, but you notice we still have R2 over R1 at the front, and then this frequency component next to it. And R2 over R1 ends up being the high frequency gain for this. So this ends up being the limiting factor of how high the output can be at high frequencies. We do the same process to find the break frequency. We find the magnitude of the gain, set it equal to 1 over square root of 2 times the high frequency gain. And when we do that, we can again get rid of R2 over R1. And now the results look similar. Again, omega R1C needs to be 1 in order to make this work. Otherwise, it won't work. So the break frequency is now 1 over 2 pi R1C. And again, we're using the one that is physically connected to the capacitor. So all break frequencies are calculated using the resistor that's actually physically connected to the capacitor, not the other one. So if we wanted to go ahead and design now an active high-pass filter with different specifications, we've got a value for the capacitor we can use, and we do exactly the same thing. The only difference is we find R1 first and then find R2 because we know the capacitor value and we know the frequency. So we can find R1 by taking 1 over 2 pi C times the break frequency, and then we can calculate that value. And again, that's not a standard value, but we'll just keep it for now. We find R2 by converting the gain value to a number, and this time we get a gain of 100, and then we calculate R2 as being 100 R1, and we get 482.3 kiloohms. We convert those to standard values of, I think, 4.7 and 470, and then we test it and do the same thing we did before, run it through LT Spice, and see what we get. And when we do that, we get mostly a nice curve. The high frequency gain is 40 dB, which is good. You'll notice I cut it off right, it's not extending as far, and there's a reason for that. But the 3 dB less than that, there's a little tiny blue arrow, which is a little hard to see, but we go over and we find that value, and we drop down, and we find that that does happen at 1 kilohertz, which is good, and we can actually sort of prove that that's going to do what we want it to do. The reason that we don't simulate this at higher frequencies is because the op-amp, the one that's being used in this simulation, can't do this. So if we were to run it at higher frequencies, you notice that it actually drops off again, and the reason for that is because of the actual op-amp. You use a different op-amp with different frequency characteristics, you can extend the frequency higher.